Hi everyone, so as I stated in my last video, the goal of this video is to show you how you can take an arbitrary path and approximate it with increasing amounts of circular motion, which winds up being something that has immense practical applications, I think, as well as a lot of artistic ones too. So first I want to say sorry for the slight delay in putting out this video. Unfortunately, I had some issues with corrupt video files, so I had to do a lot of re-recording, so you might have to forgive some inconsistencies in video quality and wardrobe. Now this video is divided into 3 parts. The first part contains all of the mathematical prerequisites that you need, and I tried to keep this portion of the video at the level of a student who might be at the end of their high school career. So if you've seen integrals, complex numbers, and maybe a dot product in your life, I think you should be okay. The second part of the video shows how you can use the infrastructure of vector graphics on your computer to take an arbitrary path that you might draw and convert it into a set of equations that you can use. And the third part goes over how you might actually go about programming this. So I do want to mention that this is an incredibly technical video, and if that's not your cup of tea, I hope you can check out some of my other videos, or maybe join me next time where I'll be doing a video about philosophy, which I'm very excited about. So the goal here is to talk about all of the mathematical prerequisites you need to do this. So let's start out with a path on the plane. So let me just draw a plane. And there's some crazy path, it overlaps with itself, it runs over itself occasionally, and then it ends where it started. So I guess I should call it a closed loop and not just a path. So one way you can think about this is as a function. So you can think about this as, there's some function f that maps an interval to this craziness in the plane. And whenever I talk about paths, the interval that they'll be mapping from is always going to be 0 to 2 pi. This is to make things consistent, and the 2 pi is there because it'll make some of my formulas later a lot easier, though it doesn't, you can do this math with whatever you want. So here you have a path. It's defined by a function f, which takes the interval from 0 to 2 pi to the plane. Now, one thing I want to say is that we're going to think about the plane interchangeably as either the two-dimensional Euclidean plane or as the complex plane. So if you remember, the x-axis can be thought of as the real axis. The y-axis can be thought of as the imaginary axis. And if you think about this picture that way, what f is doing is it's assigning the interval. So it's assigning every point in the interval to a complex number. So another thing that I definitely want to mention is that I want my loops or my paths to be nice. I don't want them jumping around discontinuously. I don't want them oscillating violently. I'm not being incredibly technical here, but I guess if you can draw it with a marker, your math will work out just fine. There are things you can do that will cause all of this to break down, but not stuff you run into naturally on a day-to-day basis. Anyways, the goal here, what is the goal? I should say right now that my handwriting is not fantastic, but I'm just going to say loudly and proudly everything I write down, and hopefully that alleviates the issue. The goal here is to approximate f, We have to think about, can we write f approximately as the sum of circular paths? So a good point to start is, what is a circular path and how exactly do I add them? So let's start there. All right, so what is a circular path? Well, I can define infinitely many circular paths very easily. So I'm going to say Vn, where n is an integer, is defined by the formula t maps to e to the n I t. So what is this? Well, let's just run through a few examples. What is V1? Well, V1 has the formula t maps to e to the it, which, if you remember, is the same thing as cosine t plus I sine t, which, if you draw it out, is just you start at 1, and you go around the circle, you go around the origin once in a circle of radius 1. Reasonable. What is, say, v minus 2? Well, v minus 2 is t mapping to e to the negative 2it. You do that. That's also the same as starting at 1. But this time you go around the origin clockwise at twice the speed. And once again, you have to recall that all of our functions map from an interval 0 to 2 pi. One other one I want to point out very quickly is what is, I've run out of room here, so what is v0? Well, v0 is t mapping to e to the 0 it, which is just e to the 0, which is just 1. So v0 is the path that starts at 1 and then just doesn't move. It stays at 1 the entire time. So you can modify these paths slightly by multiplying the equation by a complex number. So let's think about what is, what is 1 plus I root 3 times v1? So what is the path? Like, what happens to the path if I multiply it by this complex number 1 plus I square root of 3? Well, let's think about it for a second. Where is 1 plus I square root of 3? Well, I mean, there's no scale here, but let's say it's somewhere over here. This is 1 plus I square root of 3. Then you have to remember, what does multiplication by a complex number do? And what it does is it scales by the magnitude of the complex number and it rotates by the argument of the complex number. And so multiplying this with the equation of v1, what that does is that just makes your circle start here and go around the origin still counterclockwise in a circle once. I hope that makes sense. If this were instead v2, let's say it were v minus 2, then you would start here just as before and then go around the origin clockwise in a circle twice. And so that is the effect that multiplying one of these circular VIs with a complex number. Now, to get more complicated paths, you can, of course, add everything we've constructed so far. So you can think about things like, what is v1 plus, 0.2i times v minus 3 plus pi over 20 v minus 7 plus 0.6 v8. You can think, like, what is that? And what this does basically is it'll take v1, which is going around the circle counterclockwise once, and to that it will append this, and to that it will append this, and to that it will append that. So you have sort of 4 circles now rotating simultaneously, making a complicated path. And I just realized, now that I've written this down, that I can't actually draw this. So I'm just going to throw in a quick animation so you can see exactly what this particular path looks like. Now, of course, I don't want to just add random things together. I want to approximate my original path f. That crazy thing that I drew at the beginning. So the question then becomes, okay, I have these circular paths, the VNs. How do I scale each VN before adding them if I want to approximate f? And there's a very simple formulaic answer to this. And I'm going to call what you have to scale Vn by, so the complex number that you have to multiply Vn by, An. And there's a simple formula for An, and it is An equals 1 over 2 pi, the integral from 0 to 2 pi, f of t e to the negative I n t dt. Okay, that's what the formula is. This, by the way, is called the nth Fourier coefficient of f. A very, very important object in mathematics. And like I said, what you can do is now you can make a list of these circular paths. So, you multiply a0 by v0. You do a minus 1, v minus 1, a1, v1, a2, v2, a minus 2, v minus 2, a3, v3, a minus 3, v minus 3. And of course, there's, it starts at negative infinity and goes all the way to infinity. So there are infinitely many circular paths here. And the big, amazing fact is, let's say you start with this one, just a0, v0, nothing much happening. And then let's say you add 3 of them, so these 3. And then you add 5 of them, so these 5. And then you add 7 of them, so these 7. what will happen is as you add more and more of these, this will get closer and closer to your original crazy path f. Now that is incredibly, incredibly astonishing. And of course, the first question is why? Why would this work? And I think a good way to approach that question, at least initially, is to start by asking, why would anyone even guess this formula? Like, why did anyone even try to prove that this might work? Okay, so the reason that what I told you just now was a very natural thing to guess would work is that it generalizes concepts, intuitions, and ideas that you're already familiar with in a finite dimensional setting. So let's say you're working in 2 dimensions. You're working in a 2-dimensional Euclidean space, and you have a vector A, a 2-coordinate vector, A1, A2, and another one, B, B1, comma, B2. Now, one thing you might remember is that you can compute an inner product or dot product of these 2 vectors. So the inner product, or some people might write dot product of A and B, is the same thing as A1, B1 plus A2, B2. And if I were to write this with a summation, let's say it's just the sum AI, BI, where I goes from 1 to 2. It's a simple formula. You've probably seen it before. Now, this device has a lot of geometric content attached to it, and it's incredibly, incredibly useful. So let's say we're in a situation where you have 2 vectors in 2-dimensional space that both have length 1 and are at right angles to each other. So I have my 2 vectors. They're at right angles to each other, and they both have length 1. I'm going to call one of them V1 and another one V2. Now, a lot of things work out very, very quickly just by doing basic trigonometry. Number 1, because I just said V1 has a length of 1 and V2 has a length of 1, the first thing is that if you take the inner product of V1 with V1, you will get 1. The next thing, similarly for V2 actually, if you take the inner product of V2 with V2, you get 1. Now since V1 and V2 are at right angles to each other, another fun fact is that the inner product of V1 and V2 is 0. This is true for any 2 vectors that are at right angles to each other. This is actually a very easy way to test whether or not 2 vectors are at right angles to each other. You can check their inner product and see if you get 0. These 2 are actually equivalent, by the way. So if you want to test whether or not you have 2 vectors that both have a length of 1 and are at right angles to each other, you can just check these 3 formulas. They contain identical information. But there's actually more. Because if I take another vector somewhere over here, W, it doesn't matter what W is, it turns out it's very easy to decompose W as a linear combination of V1 and V2. So it just so happens that W, no matter what W is, in this situation, W is always going to be the inner product of W with V1, V1, plus the inner product of W with V2, V2. If you've never seen this before, I definitely encourage you to think about it, or if you're lazy, just look it up on Wikipedia. So when you have 2 vectors like this, it's incredibly easy to decompose any vector lying out there as a linear combination of the 2. It's very easy to figure out what these coefficients are. And what I'm going to try and convince you is that what's happening here, where that formula came from for the Fourier coefficients that I just told you about, is just an infinite dimensional generalization of this very simple picture that we already have in 2 dimensions. So let me just put the infinite dimensional picture right here. Okay, so instead of 2 vectors, let's say I have 2 paths, P and Q. So I don't know, P looks like some crazy business. Q looks like its own crazy business. They're both paths. Now, I can define an inner product of P and Q. Now, when I define an inner product in the finite dimensional case, I just summed the product of the coordinates. But since now we're dealing with infinite objects here, the natural thing to try is to do an integral. And since these paths are from 0 to 2 pi, a good generalization of this inner product is going to be, let's just integrate the product from 0 to 2 pi. So pt qt dt. We are very close to done. However, because we're working with complex numbers, the math just doesn't quite work perfectly. So I have to add a little complex conjugate right here. And I also have to scale. Otherwise, everything, when we compute our formulas, everything will just be scaled up slightly. So I want to multiply 1 over 2 pi here. So what you do is you just follow your nose and just generalize the formula for the inner product in the infinite dimensional case, and let's just see what happens. Now, immediately, one thing you'll notice is that just like this case, when you have two vectors that both have a length of 1 and are at a right angle to each other, our VIs, those paths I defined earlier, the e to the it to the 2it, whatever, you notice that if you take the inner product of Vn with Vn, using this formula, you will get 1, always. Also, you'll notice that if you take the inner product of Vk with Vl, where k is not equal to L, you will always get 0. So it seems like all of those paths, all the VIs that I made, all seem to be at right angles to each other in infinite dimensional space, just like these are at right angles to each other. Now, all this would be, you know, like a theoretical curiosity. Like, what does it mean to take an angle in infinite dimensional space? Like, well, what is this nonsense? You would be justified in arguing that this is all, you know, malarkey if this next formula also didn't generalize. But of course it does. Now, if you recall, what we said earlier is that f, you can approximate it as a sum of circular paths if you just look at, let's see, go start adding all the way from negative infinity, and you get to a minus 3, v minus 3, a3, b3, and so on. So what we said earlier is that you can approximate f as a sum of circular paths by just looking at larger and larger sections of this crazy infinite sum. Now, what I want you to notice is that these AIs are precisely, like if you remember, what are these ANs? Each AN is 1 over 2 pi, the integral 0 to 2 pi, ft e to the negative int dt, which is precisely the inner product of f with Vn. If you just look at the formula previously, this is precisely what that is. So what this sum actually is so this is the same as this, which, as you can see, is a direct infinite dimensional generalization of the formula that I stated worked in 2 dimensions, which is why this is an obvious guess that you would naturally make for how to do this. But of course, the miraculous thing is that this very obvious guess actually produces usable approximations. So I hope that made sense, but of course, there's so many details that I'm suppressing here. For example, how do you prove that this actually works? Do you actually really need all of these? Can you really take limits for these sums? I mean, there's just so many technical details that I'm ignoring. But if you're curious about them, and maybe if you're at the level of maybe like a first-year college student, I would highly recommend this book. So I'm putting it on the screen now. So this is Stein and Shikarchi's Introduction to Fourier Analysis. I read this maybe like 7 or 8 years ago. And it contains all of the details that I ignored in what I feel is like an easy, understandable way. So this is my book recommendation in case you want to dig into this further. But I think time has come for us now to dive into the practical aspects of actually implementing this. All right, so what we want to do to begin with is to take an image and extract a set of equations out of it. Now, my plan to do this was to utilize as much existing infrastructure like I already had on my computer as possible. So one thing you'll notice about this image that I drew for the previous video is that if I zoom into it, let me recenter it, then there's no loss of quality. And as I'm sure a lot of you may have already guessed, that's because this image is saved in what's called a vector graphics format. Now, what is a vector graphics format? So most image formats that you encounter on a day-to-day basis, like PNG or JPEG or whatever, the way they work is they save information about how each pixel should be colored. And the issue with that is, most of the time it works out great, but the issue with that is if you want to zoom in very far, then you basically run out of information and everything starts to look incredibly, chunky and blocky. However, the way vector graphics work is that instead of saving information about how each pixel should be colored, it saves information about how the image should be drawn. So if you open a vector graphics file in like a text editor, you'll see instructions on how to draw the image. So for instance, if you look at this little section on top of the S over here, I know that the way the computer is seeing that is as a set of numbers that it can use to construct a bunch of quadratic equations and interpolate between them. And like I said, since the infrastructure to do that already exists on the computer, it seemed to me the easiest way to accomplish this task is to just make an image in a vector graphics format, save it on the computer, and just read the numbers off and reconstruct the equations from there. I wanted to show this whole process from start to finish, so I'm going to draw something. And the program I'm using to draw my vector graphic is Adobe Animate. You can also use Illustrator. And if you want a free option, I've used Inkscape before, and it works quite well. Or if you want to be really lazy about it, you can also, just type in something space SVG into Google, and you'll probably hit something. So if you type in like Apple SVG, you'll find someone has already made a vector graphic of an apple, and you can just use that if you like. So I'm going to start by, I guess I'll make a leaf. All right, so there it is. I'm aware that I'm not Van Gogh, but I wanted to make something quick and dirty, and I think this should work. So the first thing I want to check and make sure is that the outline of this shape is a single unbroken path, which it seems to be. All right, so what I'm going to do next is save this as a vector graphics file. All right, so now that I have saved my drawing as an SVG, you can open it in a browser and see, once again, zooming in causes no loss of detail, and you have a beautiful, it's not exactly a beautiful drawing, but it looks okay. So I just remember that the process that I'm about to show you works for any drawing that you might draw, so it does not have to be this weird looking. So the next thing I'm going to do is I'm going to open the SVG in a text editor just so you can actually see the individual lists of instructions that your computer sees, and then I'll explain what they mean exactly. So let's do that. So here is everything opened in a text editor. I'm using Atom, but you can use whatever you want. You can do it in Notepad if you wanted to, but it's nice to use a text editor that recognizes XML style files, which is of course what this is. If you look at this file, there's a path, and it's the path that we want. This is our entire leaf. And to draw the path, there's a list of instructions. So you can see them, M, Q, L, QL. So like M followed by 2 numbers, Q followed by a bunch of numbers, L followed by some numbers, and so on. So M, Q, L, QL, all the way down. So this full list is a set of instructions for how to draw the path. And so each of these letters have a specific meaning, and I should say that in your average SVG file, you'll find a lot more letters than just M, Q, and L. And if you're curious about what they all mean, what you should do is you can look it up on the internet. I think Mozilla has very good documentation about how SVGs work. But since our file the only directives it has is M, Q, and L, I'll just explain what those mean because those are relevant to our purposes. So I've translated the first 2 instructions from here into plain English. And I'm going to go over them and tell you what they mean. So the first instruction, M, means move to. This is not that exciting. So move to this point, 872.7, comma, 16.15. So I've written this down here. This is not that exciting. The next instruction is the more exciting one. So instruction number 2 is draw a quadratic Bezier curve. Now, what is a quadratic Bezier curve? So quadratic Bezier curve is a parabola that is governed by 3 points. It's governed by an initial point, a control point, and a final point. But before I explain what the Bezier curve is, let me explain how to find these points in the file. So the initial point is the point that you're already at. So the point you just moved to. So the initial point is 872.7, comma, 16.15. And you can see I copied that here. That is the initial point. The control point is the next point that's listed next to the Q. So 872.3, comma, 16.55. You can see that here. And the final point is the next point. So 872.4, comma, 17.15. So I hope that makes sense. Now I should explain what a quadratic Bezier curve is. Now I think a picture speaks louder than words here. Okay, so this is just from the Wikipedia article on Bezier curves. As you can see, the red parabola is the parabola that we're after, and P0 is the initial point, the point that you start with. P1 is what's called the control point, and P2 is the final point. Now, let's actually just derive the equation for this parabola so you can use it. I should mention that this parabola starts at time 0 and ends at time 1. So at time 0, it's at P0, and at time 1, it is at P2. To derive an equation for this, what you have to do is notice that there's a green point here, you can see it, that starts at P0 and ends at P1 at time 1. So at time 0, it's at P0, and at time 1, it ends at P1. Let's first write down the equation for that point. And once again, remember that P0 is our initial point, P1 is our control point, and P2 is our final point. So what is the equation for the point that starts at time 0 at the initial point and ends at time 1 at the control point? Well, let's just write it here. So let's just do 1 minus t initial plus t times the control. As you can check that if you plug 0 into this equation, you'll get the initial point. And if you plug 1 into this equation, you will get the control point. And the intermediate t's will give you intermediate points. So this is the equation for this path. Where'd it go? The path that starts at P0 and ends at P1. Similarly, there's another green point that starts at the control point and ends at the final point at time 1. So I hope that makes sense. So what's the equation for this point? Well, it's 1 minus t times the control point plus t times the final point. I hope that makes sense. Now, what is the equation for the point that travels between the 2 green points from time 0 to time 1? After all, that is the black point that we're after. That is the point that is drawing our parabola. So once again, it is the point that starts at the first green point at time 0 and ends at the final green point at time 1. Well, that is a simple equation too. So same way, 1 minus t times the equation for the first green point plus t times the equation for the final green point. I had not intended to do this derivation, I just got excited, but I hope that made sense. And if it did not make sense, because I guess it was a little slapdash, just look up the equation, it's on Wikipedia. Just look up quadratic Bezier curve or Bezier curve in general, and you'll find this equation on Wikipedia. And then you can take your time to figure it out if you like. So anyways, these instructions, what they're telling you, so instruction 1 is move to 872.7, 16.15. Instruction 2 is draw a curve with this equation that I've written out now. And instruction 3 is so we haven't yet left this Q line. So we were here, right? This is the last point that we looked at. So instruction 3 is draw another quadratic Bezier curve. I wrote this instruction out too. So instruction 3 is draw another quadratic Bezier curve. So once again, you start at the point you ended your last instruction on. So we ended our last instruction on 872.4 and 17.15, and that's our initial point in this situation. Our control point is the next point over. So 875.7 and 66.95. And our final point in this situation is 830.1 and 71.6. And just like that, you keep drawing quadratic Bezier curves again and again until you reach the end of this line, which is right here. And then the next instruction is L, which you may have guessed is just draw a line. And you draw a line from the point where you ended your last instruction. So in this case, 370.05, 314.05. And you end your line at 370.05, 314.15, and so on. And so you just keep doing this. You just keep going down the list. I hope this makes sense. And once again, if it doesn't, this is documented in a million places across the internet, how to read these files. And once again, Mozilla has good documentation for this. And I'll put it in the description. So, you know, you just go down this list, and now from here, you actually get a set of equations that you can use. So the next step is to program a computer to do what we were doing by hand here. So let's go to that step. All right, so I've opened my Mathematica file, and this file is where this video will end. So I'm just going to write out all of my code, and you can see it in action. And I should say that I was kind of debating not including this part in the video, in part because Mathematica is not a programming language a lot of people use, and I didn't want anyone to feel like, if their preferred language is JavaScript or Python, or, if they like MATLAB, I don't want people to feel that, they need Mathematica to do this. You could program this on a graphing calculator. You could do it on a potato if you wanted. What matters is that you understand the concepts. So the way I'm going to structure the rest of this video is I'm going to write a few lines of code. I'm going to explain what they do, and then write a few more and explain what they do. And the code is going to be sort of very slapdash and hacky. I don't want to get into, the implementation of good Mathematica code. That is not what this video is about. So I'm just going to try and do this as quickly as possible and make sure the concepts are as clear as I can possibly make them. Let's do this. All right, everyone. So this is the first few lines of code. The first step is to import the list of instructions. So I just copied that list of instructions, the MQLs and so forth, and I put it in a text file called raw leaf data, and here you can see I've imported it. Actually, let's take a look at that text file that I just imported as one long string. And so here it is, and there are a few things about the way that this is organized that make it super duper annoying, and so I think what this code actually does is it pre-processes things a little bit to make this a lot nicer. So the first thing you may have noticed is that it's weird having a bunch of numbers just to cram next to each other when some of those numbers are x coordinates and some of them are y coordinates. So it'd be really nice if, these the pairs were actually organized as pairs. Another issue with this is you may have noticed that every single number is positive. And that works very well for images, but for the type of math that we want to do, it's more convenient to have all of these points sort of hovering around the origin. So one thing we need to do is, or at least it's convenient to do, you don't have to do it, is to translate all of these points so that their center of mass is basically at the origin. And then the third thing is that images have this really weird coordinate system where the origin is in the top left, which means the x-axis works like you would expect, like moving right is the same as increasing the x value. However, the y-axis is backwards, so increasing the y value in an image actually pushes you down in the image. And so we need to flip all our y values, we need to do a reflection just so that it makes sense to the computer and our math doesn't get all screwed up. And those three things, by the way, are what this little section of code does. So it does the, moving everything so it's centered at the origin, flipping the y values, and pairing the x and y coordinates. Now, the next thing I want to mention is, and actually you might remember this from earlier, but in order to make this type of format super duper compact, every instruction is assumed to start at the point where the previous instruction ended. So for example, if you look at line 3 here, it just says line and there's a point, which obviously you need more than one point to define a line. And it's assumed that if you say line point, what you'll do is you'll look back at the previous instruction, look at the point that the previous instruction ended with, and use that point to start the line. And while this makes for very compact files, it makes for very hard reading. So one thing that I would like to do is sort of, when I do my reorganization, I want to take the point that a previous instruction ended with, copy it, and paste it in the next instruction, just so that it's easier to read. So now if you reorganize things this way, this line is way easier to read. It's just like, okay, line, start here, end there. Very simple. And that little bit of reorganization for every single line is what this piece of code does. And then there are a few other minor things. Once you do that bit of reorganization where you copy the end of the previous instruction into the next instruction, you no longer need this first line. And that's basically it. I mean, there's one final line of code that takes each individual line and splits it up into its components. So for example, if you look at line 3 here, line 3 is instructing you to draw a bunch of quadratic Bezier curves. And what this line of code does is it splits it up into the individual quadratic Bezier curves and it stores all of this into a variable that I've called pieces. Let's actually take a look at pieces. As you can see, this is way more beautifully organized than this was. This is so easy to read. So, okay, start with a quadratic Bezier curve. This is the initial point. This is the control point. This is the final point. Then another quadratic Bezier curve. This is the initial point. This is the control point. This is the final point, and so on. So this is a line. This is the initial point. This is a final point. So now that we are done with our reorganization and our set of instructions is very easy to read, we can proceed further. This next bit of code is, I think, pretty self-explanatory. So I've defined the actual equations for a line or a quadratic Bezier curve, and I'm just substituting that into my pieces. So if you remember, each piece contains, so like a quadratic piece will contain the initial point, the control point, and the final point, and now I'm just putting in the actual equations for that. And I've called the variable where all that is stored piece functions, and I've already done this, so you can check. There you go, a list of equations, which is exactly what we've been wanting this whole time. One thing I want to say is that remember that in our space, all our paths are defined on an interval from 0 to 2 pi. So you're going to have to scale. So, there's like maybe, there are like 100 or so pieces to this, and so you can divide your interval from 0 to 2 pi into 100 or so pieces, and then each piece gets its each piece of the interval gets its own little function, and so you just scale appropriately. When I originally did this, I had a more complicated system where the scaling was based on the actual length of the curves. So you would, like, if there was a quadratic Bezier curve, I would compute its length, and then the amount of time spent drawing that curve was proportional to the length of the curve, which is something that you could try, but I don't think you have to do it. All right, so this next section of code computes the individual Fourier coefficients, and I have to say we're almost home. So here you can see the formula for the individual Fourier coefficients. So here you're doing 1 over 2 pi times the integral of e to the negative ijx times a piece, but then you got to add over all the individual pieces, integrating them over their respective domains. And you add that all up, you should get like, I guess, the jth Fourier coefficient. And as you can see, I have j running from negative 1,000 to 1,000, so that's about 2,000 Fourier coefficients. One thing I did is I wrote these to a file as I computed them, just in case everything crashed and burned. I would not have to start the computation over. So here is that file. So the way it's saved is it's saved in a bunch of pairs, each on a new line. And the first element of the pair is the index of the Fourier coefficient, and the second element of the pair is the actual Fourier coefficient. And then I imported that file back in and saved it as, a list of Fourier coefficients. One thing I did here that I did not do in the previous video is that I've sorted the Fourier coefficients based on how big they are. And so that means in the final product, when I actually draw the epicycles, the biggest one will be in the center and they'll get smaller as you go out. And I believe that should make for a prettier picture, but I have to say I'm not 100% sure, so we'll have to see what happens. I actually think this would be a good moment to do a sanity check. So let's actually add up the partial sum. So let's actually do e to the it times the ith Fourier coefficient and just add it up and plot it all from 0 to 2 pi and see if we get the original image back. So you can think of this plot as, what you get at the end of rotating all of the epicycles, but I'm not actually drawing any of the epicycles. So let's just see how it looks. So let's do a parametric plot where t goes from 0 to 2 pi. And what am I plotting? Okay, I got to add the ith Fourier coefficient times e to the it. So let's see, total. What am I adding? Okay, so I'm over the Fourier coefficients. Let's see, and slash at. So the ith Fourier coefficient is the second element of the pair. That's where this 2 is coming from. And e to the I times the first element of the pair, so that's the index, times t. Okay, that should do it. One more thing. So this total will return a complex number, so I need to convert that into a pair of real numbers. Let me just do that real fast. So the real part, the imaginary part. Okay, this should work. Nope. Very nice. So now we know all this works. All we have to do is draw this same plot more slowly, actually showing the epicycles. All right, so this is the last few lines. You compute the centers of each of the epicycles, circle centers, as I've called it here, by just adding one after another more Fourier coefficient times the appropriate e to the it times some constant. So you add one more, and that gives you the next circle center, and then you add another one, that gives you the next circle center, and that's basically what I've done here. Nothing too exciting here. And then you just make the graphic. So you draw circles at each of the circle centers that we've computed, and you make a parametric plot, the same one that I made earlier when I was doing my sanity check. And I don't know, I colored the background green. I'll just hit enter here, and this should work. So let's see, let's just test it. So the graphic at, let's say, time 1, it's taking a second. Ugh. I don't know how I feel about green. Okay, whatever. I'm just gonna try to pick a good color scheme, I hope. Blue is a bit darker. Okay, that's not so bad. So yeah, that's what it looks. So now you can see all the epicycles, and you can see it slowly drawing. Let me show the same graphic at the very end. So time 2 pi. No, that looks pretty good. I might zoom in just a little bit just to see. Yeah, not bad. So you can see all 2,000 circles here, and you can see it finishing drawing. So to actually just get the animation, I just have to export each of these individual frames as an image, and then I'm done. So that actually worked out pretty well. Let's actually look at an animation here. So I've exported about 10 seconds worth of frames here, and at 30 frames per second, that's 300 frames. Enjoy. All right, thank you all so much for watching. If you enjoyed that, hit the like button, subscribe to the channel, and follow me on Twitter. Peace.